Hello everyone. In this Fuel Friday video, we will talk about how canopy base height is used by wildfire behavior modelers or practitioners and discuss some of the difficulties associated with measuring canopy base height in the field.
Canopy base height is an important metric used in numerous wildfire behavior models. When referring to wildfire, canopy base height is considered as the lowest height above the ground at which there is sufficient canopy fuel for a wildfire to propagate vertically through the canopy. This threshold height is often used in wildfire behavior models such as the Canadian Fire Behavior Prediction System, Farsight, and Nexus to determine when a surface fire will transition into a crown fire. Crown fires are much more difficult to extinguish compared to surface fires, and fire managers often use these models to determine if and when a crown fire can be expected around values at risk. If the risk is too high, mitigation measures can be taken, such as conducting prescribed burns or implementing forest treatments, which will decrease the chance of a surface fire to transition into a crown fire.
We can see from these research test burns the importance that canopy base height has on wildfire behavior. On the left is a spruce tree with low-lying branches. Even with low surface fire intensity, the low canopy base height is able to support flame propagation into the canopy. The pine trees pictured in the middle and right images are not experiencing flame propagation into the canopy even with substantial surface fire. This is because these stands have been pruned and have a much higher canopy base height. Please note that the white bands on the pine trees are not natural, as this was part of an experiment that involved girdling the trees. Nonetheless, it shows how canopy base height can affect potential wildfire behavior.
We can see from these images how a critical surface fire intensity has to be reached before a surface fire can transition into a crown fire. The photos from left to right show a fire developing from a line ignition to a point where the critical surface fire intensity is high enough to engage the crowns in an intermittent crown fire. Duration from left to right is 8 minutes, and the distance is approximately 30 meters. These are jack pine trees with a crown base height of 3 to 5 meters. Based on the theory of crown fire initiation by Van Wagner, a surface fire will only transition into the crown once a critical surface fire intensity, which is based on canopy base height, is reached.
Despite canopy base height being a critical metric for numerous fire behavior models, it can be difficult to measure in the field. Theoretically, canopy base height is defined as the height above the ground where there is sufficient canopy fuel to propagate fire vertically throughout the canopy. However, what do we consider as sufficient canopy fuel load? Guesses and assumptions have been made in the literature as to what canopy fuel load thresholds should be used, but have yet to be proven practically or theoretically. Most often, canopy base height is defined by the work conducted by Van Wagner in his Conditions for the Start and Spread of Crown Fires paper. Here, canopy base height is calculated using the average live crown base height measurements for a stand. Canopy base height represents a stand level characteristic, where live crown base height represents an individual tree measurement. Live crown base height is considered to be the lowest height above the ground where live fuels have the ability to move fire further up the tree.
Unfortunately, measuring the live crown base height isn't always clear-cut and can sometimes be subjective. In many sampling manuals, it says to measure the height between the ground and the lowest live foliage of the obvious live crown, but often this isn't obvious at all. For example, sometimes there are large gaps in live crown foliage on the trees, or asymmetrical morphology where the live foliage is not evenly distributed throughout or along the tree. In these cases, is it still best to take the lowest height above the ground to represent the stand?
Although there are different ways to consider where the live crown base height begins for fire research, most suggest measuring from the ground to the height at which most live branches and twigs are continuous, while ignoring sporadic branches. Unfortunately, this still leads to some subjectivity. In the cases presented earlier, we suggest that the live crown base height should be considered the lowest point above the ground where fuels start to become vertically continuous. If measuring on a hill, height measurements should be made from the uphill side.
All that being said, there is some doubt as to whether live crown base height is really the best metric to describe when a surface fire will transition into a crown fire. For example, if we are considering only live fuels, then what about the buildup of ladder fuels on the tree itself? In some stands, live foliage can begin quite high off the ground, but the buildup of dead branches and lichen would make it easy for a surface fire to climb into the crown of these trees.
Smaller vegetation, such as seedlings and shrubs, can also act as ladder fuels that help transition a surface fire into a crown fire. Is live crown base height really an appropriate metric to determine when a surface fire can transition into a crown fire? A better way of describing crown base height may also consider ladder fuels that are in close proximity to the tree being measured. Therefore, any crown base heights would not be biased by characteristics of the trees around it. Trees growing in a dense black spruce stand often have natural pruning of the branches that are touching or shaded out by other trees. When the clump of trees is considered as a whole, the crown base height may be touching the ground, but if measured separately, we may come to a different conclusion.
Whether live crown base height is the best metric or not for determining when a surface fire will transition into a crown fire, it is often used for calculating canopy base height. Van Wagner, who developed the theory of crown fire initiation and whose work has been incorporated into numerous fire behavior models, considered canopy base height to be the average live crown base height for the stand. This has been incorporated into Canada's Fire Behavior Prediction System, the main model used in operations to predict wildfire behavior. It uses the average live crown base height expected for a given fuel type. The development of the fire behavior prediction system is based on empirical evidence, so does inadvertently account for whether or not the stand has ladder fuels.
Others have used canopy bulk density profiles to determine where the canopy base height should start. By plotting available canopy fuel in 1-foot vertical layers, a vertical distribution can be evaluated. The Fuel Calc and Fire and Fuels extension to the Forest Vegetation Simulator programs use this method. Canopy base height is determined to be the height above the ground where canopy bulk density reaches the critical value of 0.011 kilograms per cubic meter. However, this value was chosen rather arbitrarily and lacks both empirical and theoretical evidence to show that it's an appropriate threshold to use. Using this method to calculate canopy base height in conifer forests of western North America has led to an underprediction of potential crown fire behavior.
Recently, remote sensing methods have become increasingly more common for measuring canopy fuel parameters. Of the different types of remote sensing, LiDAR may have the most potential, particularly in dense forests, as it has the ability to penetrate the canopy and provide detailed structural information about the fuel layers throughout the entire canopy. However, even the utilization of LiDAR has been accompanied by limited success in predicting canopy base height. For example, models have been created by Hilary Cameron at the University of Alberta to predict canopy base height using LiDAR data in black spruce stands. The figure on the right shows a correlation between testing data and the model outputs. The x-axis represents the field measurements for canopy base height, and the y-axis represents the canopy base height values predicted by the model utilizing LiDAR. In order to satisfy the basic requirements of linear regression, a square root transformation was performed on the data. If the model was perfect and could precisely predict canopy base height as measured in the field, all the dots would be directly on the one-to-one diagonal line. The large amounts of scatter you see around the diagonal line represent the error of the model, meaning it is not performing as well as expected.
The poor performance makes sense when we think about how complex some forests are. Looking at this black spruce stand, it is hard to determine an appropriate canopy base height in person. How are we supposed to develop models to measure things that are difficult to define even on the ground? Remote sensing has been used with moderate success for other stand types, but when vegetation is relatively continuous between the forest floor and the tops of the canopy, it is very difficult to develop highly accurate models for this forestry parameter. Which brings us back to one of the main questions. What should be considered the canopy base height of a stand? In some ecosystems, the traditional assessments on a tree-by-tree basis may work, but for dense black spruce stands and potentially many other fuel types, we see that it may be more pertinent to use a holistic approach that considers other stand attributes such as ladder fuels and natural clumping.
In this video, we don't provide solid answers as to what should be considered the canopy base height of a stand, because there aren't solid answers out there. We do outline how different fire behavior models calculate canopy base height and how to perform these measurements in the field to properly utilize these models. We also highlight some of the main issues with using canopy base height measurements to predict wildfire behavior.
We would like to thank you for listening to our presentation. We would also like to thank the Canadian Partnership for Wildland Fire Science and Alberta Wildfire for organizing these fuel talks. If you have any questions or comments, please feel free to reach out. We are happy to answer them anytime.